Think you need hundreds of GPUs to do AI? Think again. AI is rapidly moving to the edge thanks to some clever microcontrollers like the new MSP M0 G5187. Curious? Then let's find out more. Without doubt, one of the most impressive technologies of this decade are the various generative AI tools everyone is using. But incredible as it may seem, it's possible to implement the fundamentals of AI, neural networks, on a microcontroller. The device in question is part of the MSP M0 microcontroller family from Texas Instruments and has only just been launched. So to find out more, I've invited Andrew Liu, their systems engineer, to tell me more. Hi Andrew, and thanks for joining me.
Hey Stuart, how you doing?
Well, thanks ever so much for taking the time out of your busy day. And before we get started, perhaps we should begin by clarifying a little terminology. I think most developers are clear on the type of AI that runs on cloud services, but are perhaps less sure what exactly edge AI means. How are they different and where are the similarities?
Yeah, sure. This is a question we get asked a lot. So with cloud-based AI, you're trying to do generic tasks like generating an image, which takes a lot of resources and time. But with edge AI, you're running models locally on MCU hardware so that you can get better latency and efficiency while still achieving simple tasks like keyword spotting and analyzing electrical waveforms for decisions on the spot.
Now, I've seen simple neural networks run on microcontrollers. I've even written one myself. Why isn't this enough? And what's needed to build a more capable edge AI MCU?
Yeah, with AI models, you can definitely still run these on a standard MCU using the CPU to do all the heavy lifting. However, when you bring in specialized hardware like an NPU, this really helps perform the AI tasks with much more efficiency, lower latency, faster execution, and this really comes through in the application benefits. This is kind of similar to if you're doing some video processing with a graphics card, which has a GPU rather than a CPU, and that's really helping process a lot of video data in a more efficient manner.
Now, the MSP M0 family has already been around for a while. It's a range of ARM Cortex M0 Plus devices that includes the smallest microcontroller in the world. Now, I've heard that you've just announced a new device, which is the MSP M0 G5187, which targets these edge AI applications. Is that correct?
Yes, that's correct. So this is a new addition to the portfolio where you have a lot of your same analog peripherals, your ADCs, comparators, DACs, and as well as many communication protocols like I2C, SPI, and UART. Now, as you start to include the Tiny Engine NPU, we're pretty much enabling AI and ML applications on many industry requirements, while also having the same performance, features, look, and feel as the rest of our portfolio.
Now, as I already mentioned, we're used to AI requiring hundreds of GPUs to understand human language and create images. I'm guessing that the G5187 is playing in a slightly different league.
Yeah, definitely. So for our MCU, we host a relatively small amount of flash with 128 kilobytes of flash on this first device. And the benefit is that you can fit all of this technology in a very small package, something around the size of like 4 millimeters squared, and consuming only milliwatts or microamps of current consumption.
What I'd like to do is go a bit deeper and start to explore that Tiny Engine NPU, that's that neural processing unit, in a little more detail. Now, I'm used to writing code from my microcontroller's processor and then executing the code from Flash and then that operating on the SRAM with all the data. How does the Tiny Engine fit into this? Does it operate in parallel to the Cortex M0 Plus and share the memory?
Yes, so it's a separate CPU basically that exists on the MCU's hardware. You have a lot of the same components in the application context. So your analog is taking measurements, your communication protocols are helping receive data into the MCU, your Flash is still hosting the code for your application and also your AI model. And with the addition of the Tiny Engine NPU, what you're doing is you're using the CPU to pass forward parameters as well as data to the NPU for processing. And the NPU can process this in a much better way than your CPU for efficiency as well as speed.
Now, as I said, it's possible to run a neural network on a standard 32-bit microcontroller. What benefit does a microcontroller with an NPU like TinyEngine offer me?
Yeah, so it really comes down to the performance in terms of latency and power consumption. So with the latency, you'll see that running the same amount of data through the model can complete the inferencing in 10x or 30x faster impact. So basically, you're reducing the amount of time that your CPU is on. And as a result, you can put the MCU in a low power state so you can save energy once the task is done.
Now, for many people, implementing an AI capability on an embedded system is still going to be very, very new, something they've never even tackled before. What is it that they need to consider before even getting started with this?
Yeah, that's a great question. We hear this from our customers all the time. So it depends on if you're starting with a model that you have in mind or if you already have just a bit of data. But basically at TI, we have an ecosystem called Edge AI Studios where you can try out some of the models we've created or import your own model, take your data, train the model, and compile it onto the hardware for testing.
Okay, so let's take a concrete example. I have a very simple single sensor. I'm gathering data and I'm clear on the features in that data that I'll be using for detection of whatever it is we're looking for. What is the actual then process for training a model that I know will always then work reliably?
Yeah, so first you're going to take the data that you have, import it into Edge AI Studios. And then as you play around with tagging the data to help it understand what kind of conclusions it can expect from the data that you provided, you can then train the model with different weights and see if the performance of the model, such as the inferencing accuracy, can it interpret it properly. Then you can adjust a few parameters and see if the performance is to your liking. And once it's okay, you can deploy it onto your hardware.
Well, it all sounds very impressive. Do you have a demo that we could look at to get a better understanding of the tool chain and the development hardware that supports this new microcontroller?
Yeah, sure. We prepared a demo for today. So basically, this is something that should hopefully be relatable to the everyday person. When you're using a phone, for example, you're trying to give input to the phone. This could be by talking to it. So it's doing some speech-to-text recognition. Or sometimes in a lot of foreign countries, you may draw a character since it's not English, alphanumeric, and that can help translate it to specific text for characters that it recognizes. So what I've prepared for today is a demo involving digit recognition, where it'll recognize some simple numbers, 0 through 9. And what I have with my hardware here is I have a Launchpad EVM featuring the device onto the actual PCB itself. We're having a connector through a USB to basically help guide the information back and forth between my laptop as well as the MCU. And what the cable is helping us achieve is it's going to load the model as well as load new data from the user for processing. So to kind of go through this example here, what I have right here is a GUI. And this interface will help us accept the user input on drawing a specific digit. So I'm just going to draw a character 2 here and see if after I send this data to my MCU, if it can understand what I've drawn.
Okay, let's give it a go.
Sure. So as you can see, we've basically been able to interpret it correctly as a 2. And when we try to run the same model using the NPU, we can see that there's a performance improvement. So what I'm going to do is I'm going to recompile a different code onto the MCU. This one is basically using the NPU for the performance improvement we talked about. And while that's compiling, we can kind of look through what this is telling us. So this first run with just the CPU took 91 milliseconds, and it was able to correctly interpret the digit I drew as a 2. Now that we have the same thing, but we're running it with the NPU, we'll see that the performance is reduced down to 6 milliseconds. So we see pretty much a significant improvement on how long the CPU had to remain on in order to get the job done.
Well, that's a serious improvement. And just to clarify again, so you're using like a development environment, I think in the web browser there, to give you the ability to input the data, so draw the image. That's then being passed down the USB cable to the microcontroller, and it's actually the microcontroller then that's running the Edge AI algorithm to do that recognition.
Exactly, that's correct. So the MCU is doing the heavy lifting. We're just using the Code Composer Studio as well as the GUI to help transfer the data back and forth and to load the model onto the MCU.
And what sort of effort needs to go into an application like this? How do you, is there a standard model available that you start with, some sort of starting point to run something like this?
Yes, that's a great question. So this specific model, the digit recognition model, is actually available now on our MSP M0 SDK, where we host code examples for MCUs, as well as the features we offer, like the Tiny Engine NPU. You can start with this model that we've already developed and basically load the data and see if the model can perform to your expectations. And that'll basically do the job.
Now, one of the interesting things here is we see this distribution graph at the bottom there, and it's obviously very strongly relating your drawn figure 2 to the number 2 as it's done its interpretation. Can you show us an example of a badly drawn figure and a digit on the screen there, and so as we can get a feeling of what other options it might come up with as it's making its decision?
Sure. Yeah, I can try. So oftentimes the user's handwriting can help make the model's performance a little bit more difficult for accuracy. So what we can do is we can try to trick it maybe with a poorly drawn 1. So for now, we'll just draw a good one, and then we'll repeatedly make it worse until the model can start to get a little bit confused. Yeah. So in this example here, you can kind of see that I've written the number 1, but it's kind of starting to look like a 7 with the tail at the top there. And the NPU, as it's running the model, is actually not sure 100% if it is a 1 or a 7. So what it'll do is it will kind of calculate the probability of each inference classification, and it will pick the one that has the highest probability and output that. Or it'll give you a result that says it couldn't make a determination from the data that you provided.
So that would mean, for example, if I were to input a letter A or a letter D or something like that, that it would then make some sort of recommendation as to I'm unsure as to what this is. It doesn't seem to be a number.
Yeah, let's give it a try. So I've just drawn a very crude form of an A, and what we can see is that it thinks it's the letter 9. So in this case, this kind of matters what kind of data set you've used to train your model. In this case, the letter A is not part of the data set that the model is ready to perform on. So it tries to compare it to the digits 0 through 9 that we're expecting. And since 9 is the closest to what we've kind of drawn here, subjectively, we pretty much see that the output of the model is a 9.
Now, obviously, this is a great demo to give us a feeling for how these things can work. In a development environment where I'm really trying to make a robust algorithm that's going to be reliable for many years of operation, I mean, what additional work has to go on? Who needs to be involved? Can an embedded software development team do this, or do they really need sort of AI experts of some sort to help them through the process?
Yeah, so we try to make it easy for all users. So if you're very experienced and you have a goal in mind, you can bring your own models and do the training and deployment that way. But for a lot of beginners that just are getting into AI, now that we've made it a lot more accessible, we pretty much can give you a lot of examples to start off with for common use cases like voice detection, digit recognition, motor arc fault detection, that sort of thing.
And one of the other things that comes to mind is I used to work with TI DSPs, and we did lots of fast Fourier transforms that allowed us to sort of detect things in the data, sort of find features in data, amplify those features. Are those things that need to be done to manipulate the data before it can even be given to an AI model?
Those things can certainly help. So with a lot of pre-processing that the CPU can do to filter out noise or help format the data into the right manner so that the model can act on it, that'll definitely help with the overall performance so that the CPU can do some of the heavy lifting while the NPU focuses on neural network calculations that it's best at.
And how does that is that reflected in Edge AI Studio as well? Are those sort of features and functions that I can draw upon in order to improve the accuracy of my model?
Yeah, we'll give some examples of that in terms of how to format the data as well as how to condition your data a bit.
Well, I must say, Andrew, it's really, really cool. I remember seeing a video of the first handwritten neural network digit recognition running on some ancient PC, and here you've gone and shrunk it into a microcontroller. I think it's absolutely incredible. I could sit here chatting to you all day, asking you questions about what's possible and how to implement it, but unfortunately we're sort of getting towards the end of our session. I have a suggestion. Why don't I do a handful of quick-fire questions to wrap all of this up? Is that all right?
Sure, let's do it.
So, question 1. Does an Edge AI application demand the use of an RTOS or a scheduler?
No, that won't be required. And this demo that I actually showed today does not have an RTOS.
Oh, wow, I'm impressed. Okay, good. Question 2. If my model becomes too complex for the Tiny Engine NPU, can I split it across the CPU and Tiny Engine?
Yes, you can adjust how the model is operated in the MCU between the CPU and the NPU. It kind of just depends on how you organize your data as well as what tasks you give to the NPU for action.
Question 3 then. Now there's different types of data. There's sort of like continuous data, like now we're talking, or a visual data from a video camera. And there's sort of captured data, which is a still image from a camera. Are there different approaches needed to developing models depending on whether it's continuous or a single moment in time capture of data?
Yeah, you have different models for these use cases. So it really depends on what you're feeding into the model and how you're expecting the model to generate an output on it. But we can give some examples of like time series classification, as well as some simple image recognition. It just depends on what you're looking for.
Great. And for our final question, where can I learn more about the AI model training and development side of the process?
Yeah, you can visit the TI Edge AI Studios, where we host a lot of our example models, talk a little bit more about the technology, as well as get you familiar with the tools in the ecosystem.
Well, that's brilliant. Thanks ever so much for your time. Unfortunately, that's it for this particular session. So thanks for taking the time to talk to me and sharing the background on the MSP M0 G5187.
Sure. Thanks, Stuart.
Microcontrollers traditionally make a series of decisions based upon hard-coded limits. However, if the data includes noise, aging, or other sources of variance, that was very difficult to accommodate, even with digital signal processing algorithms. But now the cleverness of AI is part of a classic microcontroller. Okay, it's not a GPT and it's not going to draw me a pretty little picture, but what it can do is mightily impressive, even handling recognition of handwritten digits, something that was the domain of PCs just 2 decades ago. This opens up a wealth of possibilities for embedded systems developers, regardless of whether you're looking to add new features or are under pressure to meet long battery life requirements. If you'd like to find out more about the MSP M0 family and its Tiny Engine NPU, just visit ti.com MSP M0, where you'll find a landing page with everything you need. Or you can drop by ti.com/tool/Edge AI Studio to get started with your very own Edge AI ideas.